Hey everyone! For over 200 years, Newton's laws of universal gravitation was one of the most successful theories in all of science. It explained why planets orbit the sun, why the moon orbits Earth, and why apples fall from trees. Scientists used it to predict the existence of an entire planet, Neptune, before anyone had ever seen it through a telescope. That's how good it was. But as scientists pushed it into more extreme situations, cracks started to appear. Here's a fundamental problem baked into Newton's theory. Newton's law says gravity acts instantaneously across space. If the sun suddenly vanished right now, Earth would feel it immediately and fly off in a straight line, even though we're 93 million miles away. But Einstein's theory of special relativity says nothing can travel faster than the speed of light. Light from the sun takes about 8 minutes to reach Earth. So how could gravity's effect be instantaneous? It can't. Newton's theory has no answer for this. There's also a concrete observational problem. Mercury's orbit slowly rotates, a phenomenon called precession. Newton's equations could almost explain it, but every century Mercury's orbit precessed about 43 arcseconds more than Newton predicts. Tiny, but stubbornly real. Here's something Newton did get right, but that points to something much deeper. It's called differential gravity, or tidal gravity. We know from video 1 that gravitational strength depends on distance. So when the moon pulls on the Earth, it doesn't pull uniformly. It pulls harder on the near side and weaker on the far side. That difference in pull is what we call a tidal force, and it stretches Earth along the Earth-Moon line. This is exactly why Earth has 2 high tides per day, one bulge facing the moon and one on the opposite side where the weaker pull lets the ocean lag behind. Okay, here's our first question today. If you were falling feet first towards a black hole, what would the tidal forces do to your body? Your feet, being closer, would be pulled dramatically harder than your head. You'd be stretched head to toe and squeezed side to side. Physicists call this spaghettification. Now here's why tidal gravity matters for Einstein. Even inside a freely falling elevator where you feel perfectly weightless, tidal forces are still present. 2 balls placed side by side in that falling elevator will gradually drift together because they're falling towards the same center of Earth along converging paths. You can't make tidal forces disappear by free falling. They're a signature of the curvature of gravity itself, and curvature is exactly what Einstein's theory is built on. In 1915, Einstein published his general theory of relativity. His key insight was radical. Gravity isn't really a force at all. Instead, massive objects curve the fabric of space-time itself. What we experience as gravitational attraction is really just objects following the straightest possible path, called the geodesic, through that curved geometry. Imagine space-time as a stretched rubber sheet. Place a massive ball on it and it curves downward. A marble rolled nearby curves around the depression, not because something is pulling it, but because the geometry itself has changed. And the tidal stretching we saw in the elevator, that's 2 geodesics converging in a curved spacetime. The rubber sheet is just an analogy, with real limits. Spacetime curvature is 4-dimensional and far more mathematically subtle, but the core idea holds. Mass tells spacetime how to curve, and curved spacetime tells matter how to move. And changes in that curvature propagate outwards as gravitational waves, ripples in spacetime, traveling exactly at the speed of light. No instantaneous action. Einstein's theory is fully consistent with special relativity in a way Newton's never could be. Here's a second question for you. Newton's gravity and Einstein's gravity make nearly identical predictions for everyday situations. Can you think of scenarios where they would predict something measurably different? Any extreme environment works. Near a black hole, near a neutron star, in precision timing aboard GPS satellites, or at the scale of the entire cosmos. The differences are real, measurable, and they matter. General relativity resolved every crack. Mercury's extra 43 arcseconds of precession explained exactly. Light bending around the sun during a solar eclipse, confirmed by Arthur Eddington in 1919. And in 2015, the LIGO Observatory detected gravitational waves for the first time. ripples in spacetime from two merging black holes over 1 billion light years away. And it's not just exotic physics. You use general relativity every day. GPS satellites sit higher in Earth's gravitational well, so their clock runs slightly faster than ours. Without a relativistic correction applied continuously, your navigation would drift by several kilometers every day. So is Newton wrong? Not exactly. For dropping balls, launching rockets, most planetary orbits, and even tidal forces, Newton's equations work beautifully. But when gravity is extreme, when speeds approach the speed of light, or when you need to explain why tidal effects can never be erased by free falling, why they're a signature of geometry rather than force, that's when you need Einstein. From Newton's apple to Einstein's curved spacetime, our understanding of gravity has come a long way, and future physicists may yet discover something deeper still. Thanks for watching this series on gravity. I hope you come away with a deeper appreciation for one of the most fundamental features of our universe. And remember, physics is all around you. Sometimes you just need to look at it from the right angle.